is Terry, and in this video we are going to evaluate a couple of line integrals. Line integrals are single integrals, but instead of integrating over an interval, we're going to integrate over a curve. They were invented back in the early 19th century, and they're used to solve problems involving fluid flow, forces, electricity, and magnetism. So this is the math behind a lot of what you're going to do in some of your advanced physics classes. So line integrals, like I said, they're single integrals, okay, but they're single integrals with multivariables, so we can't integrate a single integral with multivariables involved. So we have three different methods of how we are going to consider transforming these over to a single variable. All right, and these methods do utilize parameterizing based on the region, based on your base, the curve that you're traveling along. It does involve some parameterizations. So these are your formulas where we're going to take, it's pretty much the integrand in terms of x, y, and we're going to take the x and y, and we're going to take the x, y, and write them as a function of t. We're going to write them in parametric form, all right? So you'll see this through some of the examples, and so, and then this is just when you have the arc length formula as your base versus when you're dealing with your differentials. Okay, so let's take a look at a couple of examples, all right, so see how we work through this. First example, we're going to take the integral of y squared z ds, okay, and then c is your line segment from 312 to 125, all right. Because c is a line segment, then we can go ahead and we can rewrite this in parametric form. We want to take our line segment though, first of all, and this is a line segment, since you're having ordered triples here, this is a line segment in 3 space. We're going to write the equation of our line segment in parametric form, and then once we have the equation of our line segment in parametric form, x in terms of t, y in terms of t, z in terms of t, we're going to use those components to rewrite our integrand in terms of t. So let's see how this is done. So let's take our, first of all, we're going to take our curve that curve happens to be a line segment that we're integrating along. And we're going to write this equation of a line segment 3 space. We're going to write this in parametric, as a parametric form of equations, okay? So we're going to write the line segment in parametric form. To do that, if you remember back when you started your Cal 3 class, to do that you need a parallel vector, okay, and then a point. They give us 2 points, so we use one of the points, but you need the parallel vector, okay? So we need to take these 2 points representing a line segment, we need to write that in a parallel vector form. So our parallel vector, component form of the vectors come from the origin. We're going to take the parallel vector, we're going to call, let's see, 1 minus 3, okay, and then 2 minus 1, and then 5 minus 2. All right, and let's simplify that. So the parallel vector is going to be, let's see, negative 2, 2 minus 1 is 1, 5 minus 2 is 3. Here's our parallel vector, all right? So to write the equation in component form, you need your parallel vector and you need a point, okay? So your component form, all right, x is going to equal, if you remember your formulas from back in a couple of chapters ago when we started 3 space, you're going to have 3, okay, minus 2t, all right, and then we're going to have for the y component, it's going to be 1, all right, positive plus t, all right, so you have your point in your direction, and then you have z equals, and you're going to have 2, all right, and then where is it, plus 3t, all right. So here is your line segment written as equation. This is your equation of a line segment right here, written in parametric form. So what we're going to do is we're going to take the integrand of the integral expression here, and we have a y squared times z. So we're going to take the y and we're going to write the y as 1 plus t. We're going to take z, and instead of z, we're going to substitute in for z 2 plus 3t. All right, so because we can only integrate with respect to one variable, we can't add y's and z's and so on. All right. Now, so once we get the integrand set up, all right, so we'll set this up as we go. Okay, so here's what we're going to have. So we're going to set up the integrand. So the integrand, you have y squared. Okay, so again, y is 1 plus t. So let's make that substitution. So 1 plus t quantity squared. All right. Z. Okay, so what do we have for z? Z is 2 plus 3t. So 2 plus 3t. All right. And then ds, okay, so ds is your it's your arc length component, okay, so this is your arc length component. So under the radical, okay, we want to take the derivative of the x component, okay, with respect to t. So we want to take the derivative of the x with respect to t and square that. So this derivative would give you -2, so -2 quantity squared, okay. Derivative of the y with respect to t. Derivative of y with respect to t is 1 quantity squared. All right. We have a third component here, z. So you want to. I mean, this is in terms of x and y. If you do have an x and a y and a z, we do want to go ahead and differentiate the z with respect to t as well. So that will give us 3 squared dt. So here is the integrand expression. Okay. So we want to integrate. We can only integrate if you have a single integral. Got to integrate it with respect to one variable. What do you do if you have multivariables with a single integral? Well, for right now, we are going to parameterize, and we're going to write all the components in terms of t. We're going to write these in parametric form and write in terms of t. So we've got the integrand taken care of. Now we need to take care of the bounds, okay? So we need to take care of the lower and the upper bound, okay? So let's see what we're going to do to take care of the bounds. We need to go back here to our equation, okay? So we're going to take care of our bounds. Let me come over here, see if we can see. And we're going to take care of our bounds over here. Okay, so let's go ahead and take care of our bounds right here. Okay, so for our bounds, all right, we are going from 3, 1, 2, okay, to 1, 2, 5. All right. So the x's travel from 3 to 1, the y's from 1 to 2, the z's from 2 to 5, but we are in terms of t. What about t? Okay, so let's go ahead. Well, we can use the x components. Okay, so x is what, 3 minus 2t. Okay, right? X is 3 minus 2t. That's what x is. Okay, so as the x travels from 3 to 1, let's see what the t's are doing. Okay, so you substitute, so 3 equals 3 minus 2t, subtract 3 from both sides, 0 is a -2t, divide both sides by -2, so t is going to go from 0 to, let's plug in 1 equals 3 minus 2t, subtract 3 from both sides, so -2 equals -2t, divide both sides by -2, t is 1. Okay, so your t bounds are 0 to 1. That's what the bounds will be. So 0 to 1 for the bounds in terms of t. Okay, it doesn't matter which variable you use. Okay, I use the x's. You could use y's, as y goes from 1 to 2. Okay, what is y? Y is 1 plus t. All right, so y is 1 plus t. All right, as the y travels from 1 to 2, substitute 1 in for y. 1 equals 1 plus t. Subtract 1 from both sides. T is 0. All right, as 2 equals 1 plus t. Subtract 1 from both sides. T equals 1. So as y's travel from 1 to 2, the t's are going from 0 to 1. It doesn't matter which variable you use, okay? You can use any of the variables. Do we want to use z also? This might be a little bit overkill, but as z goes from 2 to 5, okay? So z, what's the z? 2 plus 3t, so z is 2 plus 3t, so z is 2 plus 3t. Well, as z goes from 2 to 5, let's solve this. So 2 equals 2 plus 3t. When you subtract 2 from both sides and divide by 3, you've got t equals 0. All right, and then when you work out over here, z is 5 over here, so 5 equals 2 plus 3t. When you subtract 2 from both sides, 3 equals 3t, divide by 3, t equals 1. So it doesn't matter if you work with the x, the y, or the z coordinates here. T is going from 0 to 1. So pick whichever is easiest for you to do. Usually I don't have to show all 3 ways, okay? So that's how you come up with the bounds of integration, okay? Parameterizing, our curve is how we're going to come up with the conversions for the integrand, okay? And that's with these expressions here. When you're dealing with a line integral, we want to see if we've got methods of taking the integral in terms of x and y, or in terms of x, y, and z. And we want to parameterize, okay? So you're going to want to write the x's and y's in terms of t. You can only have a single variable, and then after we parameterize, we're going to go through and evaluate and solve. Okay, so we want to solve, so let's go ahead, we'll square this, okay, so just solving a single integral right here, okay, so solve a single integral, so I'm going to multiply this out, so 1 plus 2t plus t squared, that's being multiplied by 2 plus 3t, okay, and then what is this radical expression? It's 4 plus 1 plus 9, so it's 4t, okay, dt, all right. And then let's go ahead, we have a trinomial times a binomial. So I'll take the radical 14 and put it up front as a constant, all right? Let me go ahead and expand this, okay? So we're gonna take, multiply each of these terms by 2. So we have 2 plus 4t plus 2t squared. Then multiply each of these terms by 3t. So you have 3t plus 6t squared plus 3t cubed, okay? Let me take a step to combine like terms. So radical 14 out front, we'll integrate in a minute. What do we have here? We have 2, okay, plus how many t's? 4 plus 3, 7 of them, okay. How many t squareds? 8 of those, all right. How many t cubes? 3 of those, all right. And we want to go ahead, let's do the next step, integrate. It's a single variable, so just integrate with respect to t. We've got the radical 14 up front, okay? Do the integration, so you end up with 2t for the first term, okay? Second term is going to be 7 and then t squared over 2. Third term is going to be 8, is going to be multiplied by t cubed over 3, and then finally 3t to the 4th over 4. Okay, we want to evaluate this from 0 to 1, our t-bounds, okay? So radical 14, we want to evaluate, so plug in the upper bound and then plug in the lower bound. Okay, so when you plug in the upper bound for t, that gives us 2 plus 7 halves, okay? Plus 8 thirds plus 3 fourths. And when we plug in the lower bound for t, we have zeros, and 0 plus 0, we have zeros there, okay? Let's get a common denominator so we can combine this. So we'll multiply everything by radical 14 when we're done. Okay, so common denominator here, 4, 3, 2, let's see, what do we have for least common denominator? It looks like we can use 12, all right? So let's use 12. All right, and let's see what we have. So 2, this is over 1, right? So we need a 12 in the denominator, so 2 times 12 is 24. 2 goes into 12, 6 times 7, this new numerator is 42. 3 goes into 12, 4 times 8, this new numerator is 32. 4 goes into 12, 3 times 3, this new numerator is 9, okay? So keep the denominator 12. Combine the numerators, so 42 and 32, okay? So that's what, 74. 74 plus 24 is going to give us 98. 98 plus 9 is 107. So 107 radical 14 over 12. So here is your solution. This is your answer. Okay. So there's example number 1, line integral. Okay. How to evaluate a line integral. So once again, before I erase the board, we're going to do one more example. Okay, so 2 examples here, but so we want to evaluate a line integral. So you got to take a look at what the curve is. In our examples today, we have line segments for curves. So we need to take this single integral and write it as a single variable, y squared times z. Okay, so we have to write it as a single variable, and you can see what the formula is telling us to do. It's telling us to take the x's and y's, or the x's and y's and z's, write them as a function of t. So if you have along a line segment, well, you can take your line segment in 3 space, and we can write line segments. You learned how to write line segments in symmetric form, in vector form, and parametric form. You want to take and write in parametric form. You want to parameterize along your curve so you can use those as substitutions to reduce your single variable down to your single integral down to a single variable. Okay, let's take a look at one more example, a little bit similar, a little bit different. Okay, so one more example so we can utilize the concept in the other 2 formulas here. So I'm going to erase, all right, and we're going to take a look at example number 2. All right, so example number 2, and again, it's going to be a little bit similar to this, same structure as this, okay, but instead of having the arc length involved here, we're going to have the differentials. All right, so we'll deal with the differentials. So example number 2, we're going to have a single integral along a curve. All right, so here's example number 2. We're going to deal with a single integral along a curve, okay? Let's deal with z squared dx, all right, plus x squared dy, and we're going to add to that y squared dz, all right? So here's our integral expression, all right? So here's our integral expression, and C is going to be a line segment again, all right, where C is a line segment, and it's going to travel from 1, 0, 0 to 4, 1, 2. So let's take a look at this example, all right? Let's take a look at this example right here. All right, so we want to take our integrand and write it as a function of t. We want to parameterize and write as a function of t, okay? So that's what the implication is here when you're dealing with these formulas, okay? So x in terms of t, y in terms of t, and we have a z component, so z in terms of t, okay? So we want to do that first. How are we going to do that? Well, again, we're along a line segment, so we're going to write the equation of the line, okay? Write the equation of a line in 3 space, okay? 3 dimensions. We have 3 different ways to write the equation of a line. Like I said, vector form, symmetric form, parametric form. We choose parametric form so we can use the parametric equations to reduce our single integral down to a single variable t, okay? So again, to write the equation, parametric form, to write the equation, we need a parallel vector and a point, okay? To write the equation of any line, you need direction and you need a point and direction, okay? So if you're in 2 dimensions, you need point and your slope represents direction, but in 3 dimensions, you need your point and you need the direction vector, you need the vector, the direction it's going, okay? So these are points on the line, okay? So we're just gonna write the parallel vector. The parallel vector is represented by the component form coming through the origin, okay? So to write the parallel vector, all right, so let's write the parallel vector for this one. 4 minus 1, 1 minus 0, 2 minus 0. So the parallel vector in this example is going to be 3, 1, 2. There's my parallel vector. And then pick one of the 2 points. I'll just pick this one right here, okay? So x is going to be 1 plus 3t, okay? Y is going to equal 0 plus 1 times t. I don't have to write the 0 there, but I did, okay? And then z is going to be 0 plus 2 times t. So here is your component, here's your component form right here. All right, so here's your component form, or here's your parametric form of your equation of your line. All right, so let's go ahead and we'll set the integrand up, and then we'll worry about getting the bounds shortly, okay? So let's set the integrand up. So we'll get the bounds, like I said, shortly, but what do we have here? Z squared, z is 2t, so 2t, and we want to square that, okay? That's being multiplied by dx, okay? So that's the derivative of the x. What's derivative of the x? It's 3, okay? Plus x, what is x? 1 plus 3t. We want to take the x 1 plus 3t, we want to square that, okay? So we want to square that times dy, the derivative of the y would be 1, okay? And then we want to take y and square it, so y is t. So y is t, we want to square the t, dz, derivative of the z would be 2, okay? All right, and so we want to reduce the integrand down to a single variable. To reduce the integrand down to a single variable, we take the curve that we're traveling along and we parameterize the equation of the curve and use the parametric form of the equation to substitute into the integrand to reduce down to a single variable. All right, now we need the bounds, okay? So we need the bounds. To find the bounds, I'm gonna go over here, okay? So let's find the bounds. So we're going from 1, 0, 0 to 4, 1, 2. Okay, so 1, 0, 0 to 4, 1, 2. And so which of these equations maybe do we want to use? It's probably easiest to use with y equals t and y equals t. That's probably the easiest one to use, right? So use the y component, y, so 0 equals t to 1 equals t. So you're going from 0 to 1. Okay, so your t bounds are traveling from 0 to 1. Okay, I know I'm way off the screen over here, so, but 0 to 1. And you can use whichever, I mean, if you want to use the x's, okay, so x goes from 1 plus 3t, x is 1 plus 3t. So as the x's travel from 1 to 4, so as the x's travel from 1 to 4, you can follow what your t's are doing. All right, so equals 1 plus 3t. So subtract 1 from both sides, divide by 3. So t is going from 0, subtract 1 from both sides. Okay, divide by 3. All right, so whichever of these coordinates you decide to use, t again is going from 0 to 1. Okay, so it's just coincidence that the last example and this example t is from 0 to 1. All right, but that's how you would figure out the bounds. All right. Okay, so now let's just integrate. We're integrating a single integral. Once you break it down to a single integral of a single variable, then you're just doing what you learned back in your first calculus class you took. Okay, so fundamental theory calculus. So let's go ahead and simplify the integrand. 2 squared, so that's going to be 4t squared times 3, so 12t squared. I'm going to have to expand this, okay? So when I expand this, I'm going to have 1 plus 6t plus 9t squared, okay? And then this is 2t squared. All right, let's collect like terms. So we'll evaluate from 0 to 1. So how many t squareds do we have? 12. 12 plus 2 is 14. 14 plus 9 is 23. 23 t squareds, okay? How many t's do we have? Just 6 of those, okay? And then plus 1. So we want to integrate these terms with respect to t, okay? So let's do the integration. 23 t to the third power over 3, okay? Plus 6 t squared over 2, so that's 3t squared plus t. We evaluate this from 0 to 1. All right? So we're going to plug in the upper bound, plug in the lower bound. When you plug in the upper bound, 23 thirds, okay, plus 3 plus 1. All right? When we plug in the lower bound, you have zeros. All right? Get a common denominator. All right? So you have 23 thirds. All right, well, 23 thirds plus 4, okay? So 23 thirds, all right, plus 12 thirds. 12 divided by 3 is 4, so get a common denominator. So keep the denominator, combine the numerators, so 23 plus 12 is 35, so 35 thirds, okay? So 35 thirds, and so here's your technique for evaluating your line integral when your curve is a line segment, okay? So when your curve is a line segment, then you're going to want to take your line segment and write your line, it's 3 dimensions, write your line in parametric form, okay? The way when you learn to work in 3 space, write equations of lines. So just like in an algebra class, you learn to write equations of lines in 2 dimensions, slope being 8-point slope, direction. You always need a point and a direction. So the point and the direction. So you learn how to write it in through space, okay? So we write in parametric form, and then we use our XYZ parametric equations. We use those to break our line integral, our integral in terms of multivariables, down to that single variable. All right, so once your line integral is of a single variable, then we can actually just, fundamental theorem in calculus, we can use our integration techniques and compute it. Okay, so I hope this helps with understanding of line integrals. I hope these examples helped. And thank you for watching. Stay safe, stay healthy. Thank you.